Lab 2, Motion of a Falling Object, Physics 2211, Section N. The primary goal of this lab was to expound upon the impact of gravity on a falling object using Newton's second law of motion. Additionally, the impact of the drag force on this object was explored in a graphical representation. Later on, we determined if the object ever reached its terminal velocity as it made its approach towards the ground. Programs such as Tracker were used to extract position data from the observed video, and additionally, VIDLE was used to create two models. The first model was one that depicted only the force of gravity acting upon the object, and a second that included both drag and gravity. In our final results, it was shown that the model depicting both the drag force and gravity was a better representation of the observed motion of the object falling to the ground. The two primary forces depicted in this lab are the forces of gravity and the forces of drag. Gravity refers to a value of 9.8 meters per second squared, and it points downward in our particular frame of reference. It refers to the force of attraction between Earth and the given object. Drag, on the other hand, acts opposite to the force of gravity. It is calculated using the object velocity as it falls to the ground. The force of drag is equal to a constant, negative b, times the velocity. Another key component of this lab, terminal velocity, occurs when the magnitude of the drag force is equal to the magnitude of gravity. It is displayed in the second model. As time increases, so does velocity. When the net force is equal to 0, terminal velocity has been reached. And when an object actually reaches terminal velocity, it is said to have a constant velocity. As an object is in free fall toward the ground, and the slope in a graphical representation of the object has a constant iterative slope, the object has said to reach terminal velocity. Moving on to the actual lab, the object that we analyzed being dropped was a paper ball. The ball contained a dimension with a radius of 0.27 meters and weight a total of 0.45 kilograms. Here, moving on to Tracker, here is the object falling from a height of a door frame. The door frame was used as a calibration stick, and the axes were tightly tilted in order to match the falling object's motion. The positive x was shown to go to the right, with the negative x going to the left. The negative y was going in the downwards direction, with the positive y going upwards. The positive z was going into the screen, while the negative z was going out of the screen. The position data from this falling object is later observed and tracked in Tracker and then put onto a table. In the table, the y position increases as time goes along, and later this is shown in a graph of position versus time. As you can see, later on, the object reaches a constant velocity between each iterative time step, and this shows that the object has reached its terminal velocity. Once again, as time increases, the y position increases in the negative y direction. This data will later be compared to the two graphical representations of gravity and then gravity plus drag later created in VIDLE. Here, in VIDLE, we set the ball's initial mass to 0.0045 kilograms. Additionally, we set the ball position to the vector 0, 0, 0, and the initial velocity to 0, 0, 0 in all directions. Additionally, time step of 0.03 is set, and a proportionality constant g for the magnitude of the weight force is set to 9.8. Lastly, the j-hat vector of 0, 1, 0 is created as the y-axis is the only component that is viewed in this lab. Proportionality constant b is later used for the magnitude of drag force in the second model. Here is the motion prediction and visualization for the calculations with only gravity. We use a reiterative while loop set with the time of 0.603 seconds, and we set the value for the weight as negative ball mass times the magnitude of gravity times the direction j hat. This weight is set as the net force. And again, just as in the previous lab, we calculate velocity and use this velocity to calculate the position of the ball as it moves along downwards. In stark contrast to the code for our first model, in the second model we have added a drag force. The drag force is calculated with the y component speed squared. This new drag force is later on added to the weight force calculated earlier to give a new net. In VIDLE, here is a graphical representation of the second model, including both drag and gravity. As you can see, we have a similar graph as the one from the observed data from Tracker. Here, in the graphical representation, the force of gravity is shown, but a force of drag is also shown. As the ball is falling to the ground, an ever-increasing drag force is shown as the ball reaches and eventually reaches terminal velocity. Moving back to the first model, here's the graphical representation versus the observed data versus the predicted with gravity. As you can see, with the prediction with solely gravity was a lot faster than the one observed from Tracker. There was a clear discrepancy from the beginning to the end, as the ball with gravity predicted the ball to fall at a faster motion, as it did not account for the drag force. In contrast, the graph depicting position versus time of gravity plus drag was much closer to the observed Tracker data. It was very close, but until it veered off at 0.6 seconds, where the observed data actually fell faster than the predicted gravity plus drag model. It is safe to assume that the gravity plus drag model is a greater and more accurate representation than the one solely of gravity. A constant slope after the 0.5 second indicated that the terminal velocity had been met. A graphical model showing the ball being thrown downwards as opposed to being just dropped shows that terminal velocity was met much quicker than just with the ball being. In conclusion, acceleration due to gravity results in a gravitational force acting upon an object. Earth's air creates a turbulent drag force opposite to the motion of gravity. The final terminal velocity is obtained when gravity and the drag force are equal in magnitude. The observed position data resulted in values larger than the gravity model, but values that were still close, but still not equal to the gravity plus drag model. This can be attributed to the imprecise markings in Tracker due to blur and not 100% calculation of drag, and movement in the x and z direction. Although the drag force model was not exact to the observed data, it did a great job of predicting the data and showcasing the object falling as it reached terminal velocity. Thank you for your time, and I hope you've enjoyed this video.